Professor Varalakshmi. Welcome you all to Operating System Paging Lecture Part 2. This is in continuation with the Paging Lecture Part 1 series. So, with respect to the previous lecture, we had seen the basics of paging and how the operating system carries out the mapping between the logical memory address and the physical memory address. And finally, we ended up with the hardware support being taken up by the operating system towards implementing this mapping. So in continuation with the topic, we need to explore regarding the hardware support provided by the operating system. So with respect to the hardware support, if you see, every operating system, it has its own way of storing the page tables. So each operating system differs in its manner in which it is trying to create the page table and store it. So most of the operating system, it tries to allocate the page table for every process. For each and every process created, one page table would be maintained by an operating system. And by default, in order for the operating system to identify or to have a track of the page table for the particular process, in other words, a manner in which the process and the page table is getting binded is by a pointer. So as we all know, every process has a process control block which stores the process ID, the stack, heap information, and all the registers related to the process, the basics. So a pointer to the page table is going to be maintained in the so-called process control block of every process. So this is how the page tables for a particular process is getting correlated. This is how the operating system binds the page tables to the process. So basically, when we try to analyze the process control block, we can easily get to know the page table for that particular process. Now, coming to the next topic regarding the hardware implementation of the page table. So which particular component of the system is going to be used in order to implement the page table? So the moment we talk about the hardware implementation, a common component that comes to our mind is nothing but the registers. So a page table, of course, it can be implemented as a set of dedicated registers. But the only concern or the constraint that needs to be satisfied is nothing but these registers need to be a really high speed registers, because the processing speed is way high, and we all know that the processor needs to take up multiple programs. It should be able to perform multitasking at the same time. So if the register speed goes down, it's very difficult to handle the pages. It's very difficult to retrieve the pages quickly from the physical memory and thereafter continue the execution of the instruction. So if in case a certain operating system decides upon taking up the registers as a storage medium for the page table, then registers need to be very high speed logic registers. And another drawback with respect to using registers for the page table entry is with respect to the size of the page table. Nowadays, since the memory size is also way high and the processing speeds is also multifold, obviously the page table size is too high. So almost it is 1 million entry per page table, in which case the normal registers wouldn't suffice for this particular size over there. That's why, though fast registers are available, okay, it's not going to be feasible in order to store huge sized page table. So in order to overcome this problem, page table base register was developed. So the so-called page table based register just stores a pointer to the page table itself. So we'll try to correlate things now. Whenever a process is being executed, instructions are going to be developed. These instructions are going to be given the logical address. And with our understanding of paging, the logical address is the instructions, the bytes are going to be divided into pages. And the information regarding how these pages are getting mapped to the frames, or rather, the respective mapping between the pages and the frames is being stored in the page table. So now we are typically over here. We are trying to understand which part of the hardware can be used for storing these page table. So we have seen registers are not going to be useful since it is way slow, and even if you go for fast registers, the size is not that compatible with the current configuration of the system. So the approach used over here with respect to page table based register is the whole page table is being stored in the main memory. So rather than storing the page table in registers or different components, we try to store the page table itself in the main memory, and we try to maintain a pointer to this particular page table in the main memory. So that is nothing but the PTBR. So PTBR points to the page table in the main memory. So the PTBR holds the base address for the page table of the current process. Whichever process is being executed, its page table is being stored in the physical memory, and that address, the physical memory location wherein exactly the page table has been stored, that is being stored in the page table based register. That's why we call it as a pointer to the page table. So it is basically a processor register which is again maintained by the operating system. So this is a diagrammatic representation of the PTBR. So if you see here, we have a page table, okay, which basically stores a page number and its offset, and similarly frame number and the offset. So the page table will be having an entry for the page number and the frame number. As we all know, the logical address is a combination of page number and offset, and physical address is a combination of frame number and offset. So page table stores this page number and this frame number mapping detail. The mapped combination is going to be stored over here. And basically we have the PTBR, page table base register, which stores that physical memory address wherein this page table is stored in the physical memory. Yes. So though this sounds to be quite convenient way of addressing a page table or trying to store and retrieve the page table, one of the major disadvantage associated with the PTBR usage is again indirectly to be said, we are trying to access the physical memory in order to retrieve the page table itself. So the problem is like, before we try to access any particular page or any particular frame rather for the particular process, first and foremost we need to access a page table of that particular process, and then thereafter identify this page number and the frame number combination, then move to that particular location in the physical memory in order to locate a specific instruction. So it is almost like accessing the physical memory twice. Once for this page table through the PTBR, page table based register value, and then having accessed the page table, we retrieve the respective frame number. Through the frame number, we try to predict that instruction from the physical memory. So it is like double the access with respect to the physical memory. So at times it so happens this is going to reduce the speed of the performance of the system, because it is like twice we are trying to access the physical memory, so it might affect the processing speed of the system. So now, in order to overcome this drawback, the concept of translation look aside buffer came into picture. So to put in very simple terms, translation look aside buffer is nothing but a cache memory. It's like a cache. So what it does is, whenever a particular page has been accessed from the physical memory, it tries to store its detail. So what happens for, say, if a page number, okay, in this particular page table, if a particular page number 3 is mapped to frame number 4, then whenever this page number 3 or any instruction related to page number 3 was retrieved from physical memory, immediately this information is going to be cached in the translation look aside buffer. So at next time, the very next time, whenever the processor tries to access the same instruction, it need not go for referring into the page table which is stored in the physical memory. Rather, it's readily available in the translation look aside buffer. So basically, if you see, the translation look aside buffer consists of two parts now. A key, also called as a tag, and a value. So it is like a key value pair. This key refers to the page number which was accessed recently and its corresponding value. So what happens here is, yes. So what is this diagrammatical representation will be more easy to understand. So as we all know, the processor is going to allocate the logical address, which is a combination of page number and the offset. And then this is a page table, right, which is going to have the details of the page number and the frame number. Thereafter, we have the translation look aside buffer internally. The TLB, the diagram, it stands for the translation look aside buffer. So this translation look aside buffer is going to have the page number and the respective frame number. So it refers to the page numbers which were accessed recently by the processor in order to retrieve any particular instruction. So whether the page is there in the cache, suppose a processor is trying to access the next instruction. First it goes and check if the page is available in the cache. If it is available in cache, it doesn't go for retrieving the page table from the main memory. Rather, it tries to access directly the frame number, and from there it goes to the physical address directly, which means here it is only retrieving once. It is not double retrieval. It is not trying to search for the page table in the physical memory, but directly it is able to access the frame from the physical address. So with respect to the translation look aside buffer, we have two things associated now. One is translation look aside buffer miss. Next one is translation look aside buffer hit. So what is meant by hit and miss? Obviously, if the processor, if your operating system is able to locate a particular page in the translation look aside buffer, the work is quite simple. As I was mentioning just now, the page details is available in the TLB, so it need not go for picking the page table from the physical address. Directly it gets a frame number, goes and access the particular instruction from the physical memory. So it is a hit now. The page is available in the cache. It has been previously retrieved for some reason. So the page is available in the cache and the retrieval goes quite easy. So this is TLB hit. On the other hand, when the operating system tries for searching a particular page number in the TLB, and obviously if it is not present, it goes for miss. So page miss in the sense, as I was mentioning till now, if it is not available, then it needs to go fetch the page table from the physical memory, locate that particular page number, identify the respective frame number, then go to the respective frame number in the physical memory and retrieve the instruction. So that is nothing but the page miss. So finally, the performance of the translation look aside buffer, it depends upon the hit ratio and the miss ratio. So an 80% hit ratio means that the desired page number was available in the TLB 80% of the time. So if it takes 20 nanoseconds to search the TLB and 100 nanoseconds to access a memory, since the particular page number was available in TLB, it is going to be quite easy. So totally it takes only 120 nanoseconds in order to retrieve the particular page. On the other hand, if it was a miss, that means obviously first the page table needs to be retrieved from the physical memory. We need to locate the page table from the physical memory, which will take certain time, then the frame number, right? So in order to access a TLB, to identify it as page, it is 20 nanosecond. To locate the page table, it is 100 nanosecond. And thereafter, to locate the exact byte in the physical memory, it is 100 nanosecond, which counts up to 220 nanoseconds. Obviously, when it is going to be a miss, right, the time taken is more. So this can be calculated using a memory access time formulae. A small formula has been generated for this with respect to the hit ratio, the TLB access time, translation, Lookaside Buffer access time, and M stands for the memory access time. So using this, we can just calculate this and identify what would be the hit ratio and the miss ratio. Based on that, the effective as access time. Yes. So the next topic in sequence is nothing but the protection. Now all this time we were discussing about paging, how the pages can be created, how it can be stored in the memory, loaded and retrieved from memory for executing the instructions and stuff. But what about the protection with respect to the pages created? How well it is going to be handled? Protection with respect to the pages means what? For example, certain pages can be only read by the system. Means the access right with respect to the page differs. And certain pages can be read as well as written. Means read-write permission has been provided. And for certain pages, it is only read-only permission. So how far the operating system is going to take care of this protection mechanism? How is it going to protect the pages from the access with respect to the access permission, which means again the pages which are read only cannot be written, right? So that has to be taken care. So no writes can be attempted to the pages which are just read only. So in order to take care of this particular concept, every page table is going to maintain an extra bit information in the page table. So it is like valid, invalid bit combination. So every page, if you see over here, it has one more column. The page table, it has one more column. As I kept on telling from the beginning, the page table is outside values represents the page numbers. The first column inside the page table represents a frame number, and the next column in the page table is going to be highly dedicated to the valid, invalid, detailed information. So what is meant by valid, invalid bit information now? There are two perceptions to this, or rather two meanings to this valid, invalid bit values. So whenever I set a particular page numbers value to be valid, it means that page is highly available. Okay, it is the respective logical page of that particular process. This is one meaning with respect to that valid bit. Second thing is it is available over there and it can be read only, or all the access rights has been taken care over there. The moment when I tell it is invalid, three things goes into picture. One is either the page is not available in the current space over there. It is not the appropriate page of that particular process. Second thing is it is not currently available. And the third thing is some protection mechanism has to be taken care. The access right has to be taken care. And one more added on to this is it can also go with respect to the frame. When I tell it is invalid, it also means that might be this particular frame is not allocated for this particular process. So by chance, if due to some reasons, okay, when this mapping is happening, if some particular page gets mapped to the frame number 6 or 7, it is an error which has to be handled. So this is not acceptable over here. The 6 and 7 frame numbers, page numbers cannot be mapped to the frame numbers over here. 6 and 7 frame numbers cannot be allocated for this particular process. So that also holds good with respect to invalid bit. Yes. So the next concept is with respect to shared pages. So this is a very small concept and a very basic concept with respect to paging. Uh, it is highly related to handling the pages in a more efficient manner with respect to the processes. So as we all know, multiple processes are going to be created in the system, and each process is going to be divided into pages. Its instructions are going to be divided into pages, and the pages are going to be loaded into the physical memory for efficient utilization of the memory. Now, when multiple pages are getting stored in the physical memory, what would be a more better approach in order to handle these pages? For example, let us assume that multiple clients are working on a particular project and a part of the code is highly repeated, okay, or multiple clients are trying to access one particular folder or one particular file, and certain thing lies in common for all the clients. Every client are having certain thing in common across with respect to the project. So for example, what I've mentioned over here, if you see the text editor, okay, I'll just assume a text editor being shared upon by multiple users. So all 40 users are going to handle the text editor. So the pages, the basic pages related to the text editor, since 40 users are using the same text editor, each user is going to write certain piece of codes with respect to the text editor. So that code is going to remain the same across the set of instructions developed by all the 40 users. So now what happens? Those set of instructions related to the text editor need not be stored as 40 different pages in different memory locations. I'll repeat. So when 40 users are trying to use the text editor, okay, which has some 150 KB of code and 50 KB of data space, it's so much space which is occupying. So I just took a different way of explaining this, right? So the text editor related codes, okay, the instructions or whatever it is, when it is being shared across 40 users, the instructions related to the text editor need not be repeated, or it need not be stored in a redundant manner in 40 different physical memory location. Rather than that, what we can do is we can just have one single location, physical memory location for the text editor. We can just store it in one location, and that can be mapped to all the 40 different processes. So this is also available in shared pages. So each user's page table maps onto the same physical copy of the editor, but data pages are mapped onto different frames. Individual data pages, whose value will be changed. Okay, the data stored by the users, obviously it is going to be changed. So that can be mapped to different frames. But the basic stuff related to the text editor need not be redundant. So we can have just one user's page table, one copy of that particular editor, okay, as a single page, and that can be shared across all the 40 users. So this is basically the concept of the shared pages. So we have process 1, process 2, and process 3. Three different process, and we have individual page table for all the three process. So this is page table for process P1, this is page table for process P3, and this is page table for process P2. So when we have all these three individual processes, so what is happening, and individual page table, certain portion, okay, is just in common. For example, if we see ED1, ED2 and ED3, 3, 4 and 6. So 3, 4, 6 portion, okay, that frames, those frames are going to be stored in all the page tables, same frame number. So all these processes are going to be pointed to the same frame number related to that so-called redundant content. We need not try to create, for example, if I take ED1, okay, with respect to process 1, some instruction called as ED1 is over there. Same instruction ED1 is there in process 3. Same instruction ED1 is there in process 2 also. Now, with respect to physical memory, I need not store ED1 of process 1 in frame 2, ED1 of process 3 in frame 9, and ED1 of process 2, for example, in frame 10. This is completely avoided. So it is again a very, very efficient manner of utilizing the physical memory address space. So I just try to maintain one single copy of that page in the physical memory, and the same frame number is going to be placed in the page table of all the process, which means the same page has been shared by all the processes. So this is the concept of the shared pages.